The next theorem I will consider is related to manipulation of circuits which have a voltage source in them in a particular way. Okay. Now, the use of this may not be immediately clear, but later sometimes you can easily understand the properties of certain types of circuits using this theorem. Okay. I will call it pushing a voltage source through a node. It will be clear in a moment what I mean by this. Now, consider a node and a number of branches are connected to this node. Okay. Let us say there are n branches connected to this node, okay. And in n minus 1 of them there are these voltages with the same polarity. That means that the negative is connected to this node here. This is the node of concern. Okay. There will be other nodes in the circuit, but this is the node we are focusing on, and there are a number of voltage sources, all of them define negative towards the node, and also all of them have exactly the same voltage V naught. Okay. So, let us say this is the case, this is some contrived situation which I am using to illustrate the point. Okay. Again we have a node with n branches connected to the node, and in n minus 1 of them we have identical voltage sources in the same direction. Okay. And the nth one, it can be arbitrary, it can be anything. Now, let us say we have some reference node, I will show it like that, with respect to which we measure all the voltages, all the node voltages. Okay. And let us say the voltage at this node is some V n. Okay. Now, what will be the voltage at this particular node? That is between this and the reference. Again, to repeat myself, voltage is always measured between two nodes. So, when I say voltage at a particular node, it means that the voltage between that node and the reference node. Okay. So, the reference node must be specified beforehand, so that this statement is meaningful, a statement such as what is the voltage at a node. Okay. So, now the voltage between this node and the reference node is V n. What is the voltage between this node and the reference node? By a simple application of Kirchhoff's voltage law, you see that it is V n plus V naught. Okay. And then let us look at this particular node over here on the first branch. What is that voltage? It is again V n plus V naught. Okay. And similarly, you see that the voltages at all these points after the voltage source, they are exactly the same and equal to V n plus V naught. Okay. So, all nodes just above the voltage source are at V n plus V naught. Okay. So, that means all these nodes are at exactly the same voltage. Okay. Now, it turns out that if you have different nodes with the same voltage in a circuit, you can connect them together with a wire without altering anything else in the circuit. Okay. So, I will show you an example. Let us say I have a 10 volt source over here, I have 2 kilo ohm and 3 kilo ohm, and you easily see that the voltage across this is 6 volts and the voltage across that is 4 volts, and the current here is 2 milliamperes. Okay. Now, let me take another set of resistors connected to the same voltage source, maybe this is 20 kilo ohm and this is 30 kilo. Okay. Again you see that across the lower resistor we have 6 volts and across the upper resistor we have 4 volts, and the current here is 0.2 milliampere. Okay. Now, let us say we take this as the reference node. We see that this node voltage here is 6 volts and this node voltage here is also 6 volts. Now, what am I saying? What I am saying is that these two nodes can be connected together because they are both at 6 volts without altering anything else in the circuit. Now, this is a simple circuit, and what else is there? If you look at the currents through these resistors with and without this connection. Okay. Let me show a copy of this and remove the connection over there. Now, without this connection, you see that there is 2 milliamps flowing through that, 0.2 milliamps flowing there, and these are at 6 volts. And if I make this connection, forget the fact that I derived this circuit from that circuit. If you had this circuit given to you and you were asked to analyze this, you would easily see that this point is at 6 volts and the current through this is 2 milliamp, the current through that is 0.2 milliamps. Because after all, if you look at this circuit, this 2 kilo ohm and 20 kilo ohm are in parallel, this 3 kilo ohms and 30 kilo ohms are in parallel. Okay. So, we will have 2 kilo ohm parallel 20 kilo ohm, which is equal to 40 by 22 kilo ohms. And here we have 3 kilo ohm parallel 30 kilo ohms, which is equal to 90 by 33 kilo ohms. Okay. And if you calculate this voltage here, it will come out to be exactly 6 volts. Okay. So, this voltage will still be at 6 volts, and these currents, now if you look at this resistor, for instance, we have 4 volts across the resistor and 2 milliamps through that and 0.2 milliamps through the 20 kilo ohm resistor and so on. So, the voltages and currents in the circuit do not change if you take 2 points which are at the same voltage with respect to the reference node and connect them together. Okay. Now, later we will see that there is some exception to this, but for now we can consider this to be true. Okay. So, I will just say that two nodes with the same voltage, needless to say it is with respect to some reference. Okay. Obviously, both voltages with respect to the same reference can be tied together, that is, you can take a wire and short these two nodes without altering voltages and currents in the circuit. Okay. I have illustrated this with an example, and in fact, if you have a circuit like this and you have this wire over here, this wire will be carrying 0 current. Okay. The red wire, it carries 0 current. So, if you break it, nothing happens, the current will still be 0 and there will be no change. Okay. So, that you can consider as another result. If you have a wire which is carrying 0 current, you can cut it off without altering the voltages and currents in the circuit. Okay. Because if you imagine Kirchhoff's current law equations at either node, they will be exactly the same if you cut this wire off or not, because if you have this wire, only 0 current was flowing through it. So, the current through this 2 kilo ohm resistor equals that through the 3 kilo ohm resistor. If you open this wire, then clearly these two currents have to be equal to each other. Okay. So, it does not make any difference at all. Now, let us get back to what I was saying over here. Because these voltages are all equal to each other, what I am saying now is that we can connect all of those nodes together. Okay. These nodes can all be connected together. We can connect these nodes without altering voltages or currents in the rest of the circuit. Okay. Now, what do we have? Let me copy this over. Now, we have taken a wire and shorted all of these things. So, this whole thing now this entire thing now is a single node, because we have taken a wire and shorted all of that stuff. Okay. So, if I rewrite this, I will get all these branches here 1, 2, 3 n minus 1, wherever they are going to some things. I have not shown what they are, because that is not of concern. And this node here, this is the same as that node, which is formed by merging all these nodes, okay, because I shorted all of those nodes together. And what do I have? I have basically equal voltage sources in parallel. Okay. Now, we earlier said that you cannot have voltage sources in parallel unless they are of equal value. Here, from the beginning, we have defined all these voltages to be of exactly the same value. Okay. So, these voltage sources can all be connected together in parallel, and they will be equivalent to a single voltage source of value V naught. Okay. So, if you have multiple voltage sources which are equal in value, you connect them in parallel, the result is equivalent to a single voltage source of that value. Okay. So, this is what we have, and then this point is what I originally said had a voltage of V n. This is the node of concern, and it goes to some branch, the nth one over there. Okay. So, what do we finally have? If we have a node with n branches, and let us say n minus 1 of them have this voltage in the same direction and of equal magnitude, then it is the same as having that voltage in the single branch, the nth branch in this way. Okay. So, these two are exactly the same as each other. Now, the more interesting thing is to go backwards, which is to say that let us say you have a node with n branches, I label them 1, 2, 3, n minus 1, n, and one of them has a voltage source V naught in this direction. Okay. Now, this can go to anything, it does not matter what is there, it could be a voltage source, current source, any component you want. Similarly, these branches can also have any components. Okay. These are just wires going to some place, but you have a node where n wires are connected together. Now, going backwards from how I reasoned out earlier, I will say that this is exactly equivalent to having a voltage source V naught in every one of these branches, okay, other than this one. Okay. We started from this and proved that it is the same as this, but the more interesting thing is to go from here to there. You can see that in this case, this voltage source has been pushed into this branch, that branch, that branch and that branch to get this. Okay. So, we take this voltage source, push it there, push it into that one, push it into that one and push it into that one, we get this particular picture. Okay. And that is why this theorem I originally titled it pushing a voltage source through a node, and that is exactly what if you have a node with a number of branches connected to it and one of the branches has a voltage source, that voltage source can be pushed through the node into all the other branches. Okay. a voltage source connected to a node can be pushed into all other branches connected to that node. Okay. So, that is the result, and this result is sometimes useful for quick and easy understanding of certain type of circuits, and it is also useful for certain types of circuit analysis and proving other circuit properties and so on. Okay.